every week. So we are already getting dozens of signals in the next few months. And several upgrades of LIGO have been planned. So it has not reached the design sensitivity yet. So as the design sensitivity increases, you will be able to see larger and larger parts of the universe with significant detections. And hence the number of detections that we can expect every year would increase as the sensitivity progresses. So we are going to have a very rich data set which have information constraining different aspects of fundamental physics, astrophysics, and cosmology. And more interestingly, for the Indian community, there is a project to build a LIGO observatory in India. This project is called LIGO India, and this is important due to a number of reasons. One is that if you remember the very first plot of the gravitational sky that I showed, I told you that we are unable to measure the sky location of gravitational signals very precisely. The reason is that gravitational detectors are like broadband antennas. You are not able to point these detectors to a particular point in the sky like a telescope. In fact, they are sensitive to signals coming from almost all directions of the sky. It's a good thing in the sense that you can basically detect almost all gravitational signals coming from all directions using a small number of instruments. But the bad side is that you are not able to locate the arrival direction of the source very well. And this can be done by combining the data from multiple detectors that are geographically separated. So what you do is, you know that the gravitational waves travel at the speed of light, and by looking at the delay in the arrival time of the signal at multiple detectors, you can triangulate the location of the source in the sky. And for this, it's very important to have the detectors as widely separated as possible. And that's why LIGO India is going to make a major contribution, because all other existing detectors like LIGO, Virgo, and the upcoming detector called Kagra in Japan, they are all located in the northern hemisphere. And an Indian detector would add a different point, the baseline of this network of detectors, which are very different from the existing detectors. So the LIGO India will significantly improve the ability with which we can localize the source in the sky, and also to extract other information, such as the polarization of gravitational waves. So it would play a major role in enhancing the scientific potential of this international network of gravitational wave detectors. But also for the Indian community, it's a great opportunity, because it's a really exploding field that is expecting a number of major discoveries in the next several years. It's really exploding with lots of data and very interesting data. And it also involves cutting-edge technology in different fronts, including optics, lasers, control systems, mechanical engineering, computing, etc. So it's a challenging experiment, both in terms of theory as well as experimental techniques, both in physics and engineering. Also very rewarding in terms of the astronomical data it generates. So, and the Indian community has an opportunity to be a major player in this rapidly exploding research frontier, and that's why we have to be really interested in this one. So it's a joint project involving the LIGO USA and the Indian funding agencies, and it is jointly run by, the Indian component is led by 3 institutions. One is the Inter-University Center for Astronomy and Astrophysics in Pune, and the Institute of Plasma Research in Gandhinagar, and the Rajaramana Center for Advanced Technology in Indore. And this project is progressing, although it's very challenging. One has to admit that it's a very challenging project, but it's a very, very demanding project. But also it's very ambitious also. One has to take challenges to go to the next level of progress. So, and if all goes well, it is expecting a target operation by 2025 or 2026. So if you are interested in contributing to this project and learning more about this, please look at the Facebook page of LIGO India, as well as the official page of LIGO India, whose URLs are given here. And I want to stress that this is an engineering institution. This is a project that involves cutting edge in physics and as well as engineering. So there are several aspects where engineers make major impacts in building this detector, including the control. It's a very, very challenging control system problem because you have thousands of degrees of freedom that have to be controlled for this instrument to be locked and maintained in the scientific mode. And also, it's a very difficult mechanical engineering problem because you have to isolate this detector from a number of environmental sources, including the seismic motion, acoustic vibrations, and so on. So, very sophisticated mechanical engineering problem. It also involves cutting edge in electronics and optics and so on, and laser technology. So, there are a variety of ways in which young scientists and engineers can contribute to this exciting frontier. So let me stop here by flashing a quote from Kip Thorne, one of the founders of this field. Thank you very much.
Questions, if any, can be asked now.
What is the significance of this observation in DSU department of mathematics? You mentioned
Right.
what way it is related?
So DAE, apart from doing atomic energy research, also funds several fundamental science projects in India. For example, TFR is funded by the DAE. Right, yeah. So this is jointly funded by the DST and DAE.
This one more question I have. This theory with the particular particle speeds up with the speed of light. Its weight increases.
Sorry, no?
Its weight is equivalently increased. If its mass is
Right,
increased,
yeah.
where mass is increased.
Yeah.
So physically, whatever you are telling, because of increase in mass, because of velocity of they are running at the velocity of light, or they are physically that mass exists. What is that?
You're taking the mass of the black hole or the mass of the particles?
Whatever particles you are talking.
So we don't have a particle theory of gravitational waves. So the gravitational waves, Einstein's theory is a purely classical theory, which does not talk about a particle picture, which is analogous to the Maxwell theory of electromagnetism. So if you want to people conjecture that there is a quantum particle called graviton, and a proper description of this would require a quantized theory of gravity, which people have not been successful in finding a quantum theory of gravity yet. So all the description that we are using to describe gravitational waves is purely in terms of waves. But because the gravitational waves travel exactly the speed of light, which also have been observationally constrained also, the corresponding particle of graviton has to be massless, just like photon.
Actually, I had the same question. Is the equivalent of slit experiment for gravitational waves? I think partly.
Yeah, actually it is. It is. You can do a slit experiment, which shows the wave nature, and this has not been done yet. But in the next few years, we expect to see it. So what we just need to see is the indifference of two waves, right? And this is bound to happen in a number of ways. One is that as the number of observations increase, we will be detecting gravitational waves every hour or so. So the probability of two signals colliding at the same time and overlapping becomes negligible in the next 5 years. Then you would see indifference of physics. There is also more dramatic ways in which this can happen. One is called the gravitational lensing of gravitational waves. So if you have a massive object that is bending the space-time, just like light, gravitational waves also bend. Then you can have multiple gravitational waves bend and combine, producing diffraction, interference, etc. So such kind of wave optics phenomena also we expect to see them in the next few years.
The second question is there any energy decay associated with gravitational waves?
Just like electromagnetism. So in fact, so in the absence of any interaction, the electromagnetic waves goes as 1 hour distance, right? The amplitude of electromagnetic waves goes as 1 hour distance. The same thing happens with gravitational waves. And in fact, so the one major difference with electromagnetic waves and gravitational waves is that gravitational waves hardly interact with matter. They are not scattered, they are not absorbed, so they just go through everything.
Any other questions?
Sir, how much do you validate wormholes?
So the wormholes is a proper mathematical solution of Einstein's equation. So mathematically they can exist, but the physical existence of wormholes would require certain kind of exotic matter, which would violate some fundamental energy conservation principles. So most of the physicists do not believe that wormholes would exist in nature.
mentioned that with the detection of gravitational wave, we came to know about the existence of some supermassive black holes. So does it give only information about the existence, or does it give any other information like properties of black hole like X-rays does?
Oh, well, no, yeah, we can actually measure properties of black holes, including their mass, their spin angular momentum, etc. Like we can measure their mass fairly well. We can measure their spin angular momentum, not that well, but eventually we'll be measuring their spin angular momentum very well also. And we believe that these are the only properties that black holes has, but we can also test whether they have other properties, or they are indeed black holes that is predicted by Einstein's theory. So they are part of these tests of general relativity or black hole that I mentioned briefly earlier. So these signals contain a wealth of information.
Can we artificially create this gravitational waves, or is it by?
You can, because any motion of masses will produce gravitational waves.
No, question is
Yeah.
related to that observation that after some time from
Right.
space they will
Yeah.
collide near Earth.
Yeah.
Is it possible to divert?
It's a,
Is it possible to divert them?
using gravitational waves? No, that will be the bad way, because the gravitational waves do not interact with matter. So if you want to, shoot some radiation, I would bet on photons, not gravitational waves.
So there may be some simultaneously coming gravitational waves, right? So how do you correlate that one with the mass of a particular, like the properties?
Yeah, so currently we are not in a regime yet, because we are still observing one gravitational per week or something. So the probability of two signals coming at the same time is very small. But eventually we will be in a regime. But still you can, there are data analysis methods that you can use to separate them and so on.